Hello everyone, I'm Dogyun Park, a graduate student in the NLB lab at Korea University. Today, I'm excited to share our recent work, Constant Acceleration Flow, which has been accepted at NeurIPS. To start, I will provide some background on rectified flow. Rectified flow introduces the concept of a time-dependent velocity field defined by an ODE with respect to time that transforms an initial distribution pi0 to a target distribution pi1. This ODE can be solved by integrating both sides of the equation. Rectified flow further simplifies the process by assuming that the velocity field remains constant over time, allowing for single-step generation. To make it simulation-free training, it proposes a time differential interpolation for xt, and it learns its target velocity using a neural network. In rectified flow, a key challenge is ambiguity arising from flow crossing. This induces a curved trajectory rather than the desired direct path. To mitigate this, rectified flow introduces a reflow procedure. Despite the advantages by rectified flow, there are some limitations to this approach. By relying solely on velocity fields to estimate complex transformations between distributions, we may restrict the model's expressivity, limiting its overall performance. Additionally, even with reflow, flow crossings can still occur, leading to suboptimal outcomes for single-step sampling. This issue is illustrated in this result, where two rectified flows still struggle to generate accurate target distribution. To address these limitations, we propose a new framework called Constant Acceleration Flow. Our approach is formulated through an ODE that incorporates both an initial velocity field and an acceleration field. The key assumption here is that the acceleration field remains consistent over time. Similar to rectified flow, we solve the ODE in constant acceleration flow by integrating both sides. With our assumption of constant acceleration, we arrive at the straightforward expression for single-step sampling. Compared to rectified flow, CAF includes an additional acceleration term, which serves as a correction factor, providing a more accurate solution. Our interpolation in CAF differs from rectified flow. With the initial velocity and two endpoint samples, we can generate intermediate point xt that follow the constant acceleration equation. This approach generalizes rectified flow by introducing greater flexibility, allowing us to model more flexible trajectories between distributions. To train CAF, we begin by defining the target initial velocity field as a scaled version of the displacement vector between x0 and x1. Then we train by minimizing the distance metric between the target and the estimates. Furthermore, to address flow crossing problem, we introduce initial velocity conditioning technique. In this approach, we condition the acceleration model on the initial velocity, incorporating it as an input to enhance directional awareness. By conditioning on the initial velocity, the model gains a clear sense of directionality, reducing ambiguity at intersection points like xt. To further evaluate the scalability of CAF, we conducted experiments on real datasets, including Cypher10 and ImageNet. The results shown in the tables indicate that CAF achieves better or comparable performance compared to the state-of-the-art models, even when using single-step generation. An important property of constant acceleration flow is its ability to preserve coupling between deterministic pairs. In this analysis, we evaluate how well CAF maintains coupling. The results shown in the visual examples and the metrics table indicate that CAF achieves superior coupling preservation compared to rectified flow. This is due to initial velocity conditioning, which enhances directional consistency. An interesting property of CAF is its ability to perform accurate single-step reconstruction through inversion. This capability is highly beneficial for real-world applications such as image editing, where efficient and precise reconstruction is essential. The comparison shown here demonstrates that CAF achieves high-quality reconstructions closely matching the ground truth images in a single step. To conclude, constant acceleration flow introduces a novel ODE framework that enhances rectified flow by incorporating a constant acceleration term, leading to improved accuracy and efficiency in generative tasks. Thank you for listening. For more details, feel free to scan the QR codes to access our GitHub repository and the full paper.